How you doing? I'm Mr. Rose, and today we're going to start to discuss Gauss's Law. To be fair, there's a lot of background to get into Gauss's Law, so please bear with us. What do we know so far? So far, we know there are things that exist, electric forces and electric fields. I know if I have some charge at point P, and I want to find, say, the force due to these other charges, say Q1, Q2, and Q3, I've assumed they're all positive just because it makes it a little bit easier. I know I ignore Q2 and 3 to find the force from F1. Same thing with 2 and 3. I know that the force vector here obeys the law of superposition. I know I can add all those vectors to find my net force. I know that net force is the same direction as my electric field. And I know I can calculate that with a simple equation, F equals Q times E, the charge times the electric field. On top of that, I know that an electric field that I have drawn here is the direction that a positive test charge will act in the area of that electric field. I know it's independent of my test charge, and I have all my lines radiating out in the direction of my electric field. Now this dotted line here that I have, this purple dotted line, I have as an equipotential line. And I know that the equipotential line is the same amount of energy it takes to transverse around that line. It takes zero amount of energy. If I moved out or moved in, it would take a different amount of energy, but I know the same amount of energy it takes to get around that spot of my electric field. I know those equipotential lines are always drawn perpendicular to my electric field line. Next, we talked about dipoles. We know dipoles themselves have their own electric fields that I haven't drawn here. Here I drew a dipole, a positive Q and a negative pole, Q, inside of a uniform electric field. Well, I know that this charge would have to feel a force, Q times E, in this direction towards me. I know this negative charge would feel a force, negative Q times E, in that direction. But I know because it's attached by this rigid body, they can't really move that way. So since they're attached, again, by this rigid body, we would know that they're not going to move parallel, but they're actually going to start to twist and form a torque. So I defined this distance, A, as the distance from my center to one of my charges. And I recall from Newtonian mechanics that torque is just my R cross F. And I know that since I have two charges that are the same, my force is 2 times QE, that's actually my dipole, times A sine theta, where sine theta, this would be the angle theta in between that axis of rotation and what I'm assuming is that rigid spot. Again, we assume that that dipole is connected by something that can't move. Well, I can define my dipole, or I can remember that my dipole is 2 times QE, 2 times my force, times that distance A. Thus, I know that the torque of a dipole in this uniform electric field is P cross E, where P, again, is defined as my dipole. The last thing we talked about is we related things to potential energy, or energy in general. We know that energy is Q times V, and again, I can see that V is the electric potential, and Q is the charge. As that electric potential, if that never changes, my energy never changes. I get around for free. I know that's 1 over 4 pi epsilon naught, QQ over R, and that falls off as a distance of R, not a distance of R squared. Now, if we start putting some things together, we might remember that force, by definition, is negative du dx. That's the same thing as, I actually noticed that's backwards, that's the same thing as saying my potential energy final, my potential energy initial, is equal to my antiderivative from x naught to x of negative f dx. We might remember force as a dot product, which means now we can sum up energy and motion, really force and energy, or torque and energy with a dipole, as torque being a cross product, P cross E, for that electric dipole, and the potential energy of my dipole to be a dot product, P dot E, or PE cosine theta. The last thing we want to remember as we move forward are the tricks that we've utilized to this point. We always had a mass ratio that we used in the past, like a mass to length ratio. Well, here we're still going to continue to utilize those same concepts, except they'll be charge ratios. So I just want to remind us that lambda is a charge per unit length, or a coulomb per meter. Sigma is a charge per unit area, or a coulomb per meter squared. And rho is a charge per unit volume, or a charge per meter cubed. So let's get into an example that is a little bit difficult, but pulling on some of the things that we've done in the past. Let's say I have a infinite sheet. So I have this infinitely long sheet, and I want to find the electric field from that sheet that I just threw on some positive charges there at some point P away. So we're going to find the electric field. Now notice, I don't care where I put point P in this, or up and down, or left and right, because my sheet is infinite. So if I just move one space over to the left, it's again seeing the infinite sheet from all points. It'd be the same thing as moving my sheet one space to the right. It doesn't matter. We can make arguments that say that field is going to be the same. So how are we going to do this? I can't just take columns, and that would seem to be easier. But since it's infinite, I can't have an infinitely long column and do anything really useful with it. So what we're going to do is we're going to use rings, because I have the beginning and end in a ring. Now granted, my ring can go infinitely out or infinitely in, but at least I will have a continuous ring. So what we're going to do is we're going to define a ring of radius r, some thickness dr, and I want to find at some distance, P in front, some distance A in front of my sheet. And what we're going to do is, just like we've done with the ring in the past, we had a solid ring, we want to find what is the electric field due to any point that I've labeled dA here, this little pink section dA. What is the electric field at point P due to that point? We should be able to see from symmetry, just like we've done in the past, that when I look through all of these small points, and I've drawn two of them, these two, the top and bottom, I will have vectors cancel out, and I will have a net vector in this z direction, or really coming out of the board. That's what I've tried to show us here with that green vector. So my electric field, just due to one small spot, dE is 1 over 4 pi epsilon naught. Again, I utilized my cheat. My sigma dA is my charge divided by my radius, r squared plus a squared, where it's just my r squared plus a squared that far away. Again, I can see from symmetry that if I did the same exact one on the bottom, I would be able to cancel that out, and I would have a net charge just going in this direction, or a factor of, I can add a theta in there, add a theta in there, my factor of cosine theta. So that's what I've done here. All of my net charge would be coming perpendicular to that plane. My net electric field, rather, would be coming perpendicular to that plane. So what I've just labeled my field perpendicular, 1 over 4 pi epsilon naught, times my charge, sigma dA, divided by my radius, r squared plus a squared, in that cosine theta direction, a over r squared plus a squared to the 1/2 power, or to the square root of r squared plus a squared. This gets us to a point, but what exactly is dA? Because it seems like dA is really where all the meat and potatoes is. How big is that section? Well, dA, I can look at my little pink section here, and I just broke down here, is just a length times a width, 2 pi r times dr. So now I'm going to replace my dA with 2 pi r dr. I have my dE, my electric field due to that small spot up there, is equal to sigma times a over 4 pi epsilon naught, times my dA, 2 pi r dr, over, combine my denominators, r squared plus a squared to the 3/2 power. Now I'm going to sum everything up, and we know that summing that up means calculus. I'm going to pull out all my constants. I have 2 over 4. Now I know I can cancel, obviously, 2 over 4 and reduce that, and I'm not, and you're going to see why in a minute. So I'm going to keep that 2 over 4 sigma a over epsilon naught, and I'm going to integrate from 0 to infinity, because it's an infinitely large sheet, of rd over r squared plus a squared to the 3/2 power. This integral is not trivial, which is why I'm going to use u substitution. Quick review on u substitution. I'm going to let u equal r squared, because I want to figure out a du. Du is 2r dr. Now you can see why I kept that 2 in play. I could bring that 2 back in here, as you see here, and then I have a direct substitution. So to continue up here, I just brought my 2 back in, 2rd over r squared plus a squared to the 3/2 power. I substitute in my u and my du. I substitute in my du for the top, 2r dr. I substitute my u for the bottom, and I take my antiderivative. Now this antiderivative is relatively trivial. You should be able to do these by now. A couple of different ways I can do it. I can bring my 3/2 up to the top. I can use a quotient rule. I can do all sorts of fun stuff, but we should be able to see that my antiderivative, my constant stay, a over 4 epsilon naught, I canceled out my pi. Oh, sorry, I canceled out my pi's earlier. But I have a over 4 epsilon naught, negative 2, u plus a to the 1/2 power. Now when I evaluate from 0 to infinity, when I put in my infinity, that blows up and goes to 0. Yeah, that's right. And when I put in my 0, that goes away. My a is canceled. I'm just left with sigma over, drop my sigma over 2 times epsilon naught. What does that tell us about the electric field at point P in front of the sheet? What it tells us something interesting about D. It doesn't matter where I put point P in that infinite sheet. I can put it infinitely far away. I can put it close. My electric field does not fall off the factor of a distance. Now I'm going to leave that for you to try and figure out why. Maybe understand a little bit how that doesn't fall off. What we're going to continue with, however, is start and get into the next stuff. A little bit harder. What if I wanted to know, instead of just some infinite sheet or some point particle, I wanted to find the electric field of some blob of charge? Well, now, blob of charge, I'm picturing something three-dimensional. So I drew a three-dimensional sphere, because a sphere could be a blob, and things that I would need to know. I'd need to know that my charge density is a charge per unit volume, so I'm going to need to remember Coulomb per meter cubed, so I know that my charge is just some rho times my volume. Then it's going to get hard. I would need to start being like Isaac Newton, the way he dealt with gravity. I'm going to need to start picturing this electric field that I have drawn coming out radially everywhere out of my blob. I'm going to need to start breaking that down into small squares. I'm going to need to find the electric field at every component. I'm going to need to sum up all those electric fields. That sounds like it's going to be difficult. So instead of doing all that, we can apply a cheat. And that cheat, my friends, is Gauss's law. Now don't get excited. We're not actually going to get to Gauss's law yet, but we're going to get there through a little bit of a story. First, let's assume that after I recorded this video, or I should say before I recorded this video, as I was walking here, I saw a UFO. And I want to be able to describe that UFO to the best of my ability to everybody I know. So what can I observe? I drew my UFO here. I can observe that it's flat. I can observe that it looks kind of like it's a rectangle. So I can easily observe its area. I'm going to say its area is just dA, and I know it's going to have a unit of a meter squared. Well, what else can I define? I want to be able to define its direction, because I noticed that the UFO was going all those crazy places, those crazy different directions. So I want to be able to define its direction somehow. I can't just say up or down. I'm not so good with the north and south. So we're going to define it using vectors. What we're going to do is we're going to define its direction. And how am I going to define its direction? I'm going to define its direction with a vector, because I know that I can define a direction perpendicular to that flat surface, which will leave me only two options: perpendicular up or perpendicular down. Well, vectors don't have two options. Vectors only have one option. So to get that actual direction, we're going to apply our old friend, our right-hand rule. Here I redrew my UFO shape, and I threw in some arrows, just saying that it's going that direction. And then you can even see I can apply this right-hand rule, and now I'm defining a vector that is coming out of the board, or in my UFO case, straight up. Now I have this vector that I've defined as dA, which is a little bit weird. dA is going to be a vector. It's an area vector whose magnitude happens to be the same size as the actual area of that piece. It is now just a vector. This is one of our keys. We need to start to understand and accept that we are going to have this area vector dA. So we're going to associate areas with vectors. Once we accept that, we need to talk about the second thing that needs understanding in order to understand Gauss's law. That second thing is flow rate. So I came to work, I described this UFO to everybody, and I may have gotten fired after that because no one wants a physics teacher talking about UFOs. From there, I went to my fallback, what I've done before, and I went back into HVAC, which is something I've done in the past. So I designed this nice ductwork for airflow, and I defined this vent, or this airflow, as a rectangle, because rectangles are nice and easy, of height h and width w. And I know that as my air flows through, my fluid that's going to flow through, all of the air that flows through this section also is going to have to flow through this section, that red section there. I know the same amount of air flowing per second should be the same amount of air flowing per second there. Now you've noticed I've defined this area vector perpendicular to my plane. Well, I know that I can define how much is flowing through that spot and how much is flowing through that spot by the area. I know area is h times w, just my h times my w. And since I'm talking about a flow rate, I want to know how much air is flowing through this section, which I've redrawn down there. My air has some velocity to it. I've defined that as v times 1 second because it's easiest to do v times 1 second. So now this section, this cube, is how much fluid or air is flowing through my area times that bottom piece times the velocity. I'm going to define this flow rate with a capital omega. That capital omega, h times w times, that's not an omega, that's capital phi. H times w times my velocity v. Now I know that h times w is my area. I can say a dot v, and I can say my flow rate that I've just defined is a dot product of my area dot the velocity. How can I show that? I can show or prove that because I know my dot product is just a factor of cosine theta. So if I look at my maximum, clearly I would have the most air or fluid flowing when it's perpendicular. When my surface is perpendicular, or my vector is parallel to the flow rate. So when my vectors are parallel, I know cosine of 0 gives me a maximum, gives me my maximum flow of a times v. If I take that and turn it in the same direction, now my vector would be perpendicular to that. When my vectors are perpendicular, I know the cosine of 90 is 0, therefore I would have a minimum or no air flowing through that flow rate. There's a third option. What if it's not perpendicular? What if it's not parallel? What if it's at some off angle? So here again, I've redrawn my air duct. I've got my velocity flowing through it. I know that my air per unit second, my flow rate air per second here is the same as going through the red surface area there. Well, now I've got this purple surface area, this angle, which is clearly a larger surface area. With a larger surface area, affect my flow rate per second. It's my claim that it's not going to. Well, how do I know it's not going to? I can do it mathematically, or I can understand that air or fluid gets to that point before it gets to that point. Therefore, my rate per second, my flow per second is still the same. Mathematically, I know the area of this is still W times H, and here I have some angle. It's divided by the cosine of theta. I'll let you think for a second there. It is definitely divided by the cosine of theta. This area that I've defined A naught is W times H divided by cosine theta. I know this angle here is also equal to that angle there. Why is that important? Well, I know the velocity is going this way. I know my area vector is now perpendicular to the plane, so now I know that that's a cosine of my angle. So if I wanted to do the math, I could. If I wanted to just directly plug in, I know V times A, except now it's my A naught, times cosine theta. My cosine thetas are going to cancel, and I'm just left with my flow rate is equal to V times W times H. So I can conclude that by definition, the flow rate of any vector with velocity V is going to be just that velocity times the area, that surface area. It doesn't matter the shape, it doesn't matter what it's doing, it doesn't matter what it looks like. If I know the velocity and I know the surface area of that object, I can figure out the flow rate of my vector through that system. How does that relate to Gauss's law? That's a good question, and I'm going to leave you to ponder that for next time. I need you to come back and watch the second video. That's all I have for you today. Please feel free to like, comment, or subscribe, and you will see me next time.